So this video will be the first video of several different videos pertaining to thermodynamics. And so what we're going to be talking about in this video is just some basic information referring to, what thermodynamics is about, and just covering some basic details that we need to know for future videos. And so the first thing we're going to talk about is spontaneity. And so spontaneity, well, if I can talk straight here, sorry. If spontaneity, the first thing we want to do is ask, what does it mean? And spontaneity just refers to the term spontaneous. And so spontaneous just means that it's something that's going to happen on its own without any outside intervention. So the best way we can talk about it, an example that being is if we take a nail, and you can see the nail here, if we put a nail outside and we come back to it after a few days and it's rained over that period of time, what we'll see is the nail will have this orange coating on the outside. Now this orange coating on the outside is referred to as rust, and so rust forms on its own spontaneously. Now, if we go and we ask the question that could we reverse this process, could we turn the rust back into the original nail? The answer is no, we can't do that. And so, can all processes be spontaneous? The answer to that question is no. And the reason for that being is that the rust is the example we're talking about here, where rust cannot be converted back into the original form of the nail. Now you can sand the rust off, and that itself would bring the appearance to look like it originally was, but it's not the same, because it's not the same mass. You've lost mass in this particular case. So what does spontaneous mean? It means that something's going to happen on its own. Can all processes be spontaneous? No, they can't all be spontaneous. Now, as we start to move forward and we say, and we're talking about different spontaneuses, well, some processes may be spontaneous at one temperature, but be spontaneous at another temperature. Perfect example would be ice melting versus ice forming. So as we look at this picture above here, we have ice. If we take that ice and we put it onto a table that's at room temperature, what's going to happen to that ice? It's going to melt, of course. And so ice melting, the phase change going from solid to liquid, is spontaneous whenever the temperature is greater than 0 degrees Celsius. So we see that process is spontaneous at that temperature. Now, if we take liquid water and we put it into a freezer, well, freezer obviously is below 0 degrees Celsius. Well, is that liquid water going to stay liquid at that temperature? No, it's not. So the water is going to turn into a solid at those lower temperatures that are less than 0 degrees Celsius, and is spontaneous in that direction. So phase changes are examples where it is temperature dependent of whether it's being not spontaneous in one direction or spontaneous in the other direction. So now another thing that we've got to also talk about is irreversible. What does irreversible mean? Irreversible means that something cannot go back to its original form. And so when we talk about it like that, so a reversible example would be, let's say, an equilibrium, where the reaction could go forward and it also can go in reverse. So the rusting of a nail is not reversible. Once the rust forms, it cannot go back into its original form, so we call that an irreversible process. All spontaneous processes are irreversible. That's an important point to make a note of. All real processes are irreversible, so the nail rusting being a spontaneous real process. So ice forming at lower than 0 degrees Celsius would be a spontaneous. the ice is not going to melt, because once it's formed at that lower temperature, it can't be reversed at that point. Now, the only way to reverse it is to then take it out of the freezer, put it on the table, and then it becomes spontaneous in the other direction. So it can't go backwards once it's formed either the solid or the liquid. So those are also considered irreversible spontaneous processes. So now the next term we're going to look at is called entropy. And entropy is a term that was discovered by Rudolf Clausius. Clausius studied the ratio of heat and temperature. And the ratio of heat and temperature in this case is Q over T. So the symbol that we use for entropy is represented by S. So we could write the term S, the equation S is equal to Q divided by T, where Q represents heat and then T represents the temperature, whatever temperature that might be, but the temperature is going to be in Kelvin and the heat will be in units of joules. So entropy can be thought of as the randomness of a system. I oftentimes like to say that entropy is disorder. Disorder is randomness of a system. So as we start to talk about randomness, an example being here would be the cleaning of your room. All right. And so in this case, we're going to say dust. All right. If you clean your room on Saturday and you come back the next Saturday, of course, the room is not going to be the same as it originally was once you cleaned it. You're going to have clothes scattered about. You're going to have papers. You're going to have dust even that's settled out of the air on the surface, which creates disorder. And so entropy is sort of a state of disorder in this case. And the more randomness you have, the more disorder you have, the higher the entropy is going to be. Now, entropy is also called a state function. And so entropy is a state function. Recall that a state function is a variable that does not depend on how you determine it, but the value you obtain in the final step. And so what we can form an equation here where delta S is equal to S final minus S initial. And so if I were to tell you to go to the lab and get me 50 milliliters of volume, you go to the lab, you do whatever you do, you come back and give me my 50 mils. The only thing I care about is that I got my 50 mils of water. I didn't ask you how to do it. Because there's many different ways you can do it. You can get a beaker, you can get a graduated cylinder, and there's multiple sizes of graduated cylinders that you can use. The point is that you have the initial, and then you have the final, which in this case the final was the 50 milliliters of water. And so state functions can include entropy. Entropy, remember, is heat. Delta H, entropy now, pressure, temperature, volume. And so we're going to utilize what a state function is in relation to entropy. Now, as we move into thermodynamics and discuss the different laws, the first law is something that you learned in chemistry 1, and that is the law of conservation of energy. The law of conservation of energy states that energy is neither created nor destroyed. And that's a law that just about every scientist works around and uses, and it's the first law of thermodynamics. The second law of thermodynamics is entropy in the universe. So the entropy of the universe is going to increase for a system. As we understand the universe is constantly expanding, and as the universe expands, there's more disorder, and the more disorder you have, the higher entropy that you're going to have. And so there is an equation that we can utilize and we can use, and that is delta S of the universe is equal to delta S of the system plus delta S of the surroundings. Now, this equation can be used in two different ways. We talked about reversible and irreversible systems. So if you have a reversible system, all right, this term is going to be equal to 0 because for a reversible process, it's not spontaneous. The entropy is not going to change for a reversible system. However, if you have an irreversible process, the delta S of the universe is going to be not equal to 0, but it's going to be equal to the system plus the surroundings. And this is actually going to be greater than 0 because the entropy of the universe is constantly going to increase. And so delta S for a irreversible real process is going to be greater than 0 for that reason. Now, the third law of thermodynamics, and we're going to get back to this here in a future video, but for now, let's just get it on the table here, because there's 3 laws of thermodynamics. The third law is that the entropy at absolute 0 is equal to 0. Now, I'm not going to go into details why that is right this minute, but I just wanted you to understand that there are 3 laws. These are the 3 laws that we have to focus with and work around pertaining to the laws of thermodynamics. So, just to recap here, all right, we have the entropy is based around Clausius Clapeyron equation with, not Clausius, the entropy is based around Rudolf Clausius' definition of delta S, which is equal to Q divided by T. Alright, the entropy of the universe is constantly increasing. Entropy itself is a state function, and there are 2 different types of processes. There's reversible and there's irreversible processes. So if we work with irreversible processes, they are considered to be real and spontaneous. And we know that entropy is thought of as the measure of disorder, the randomness of a system. And this randomness is based off the motions of those molecules. So as we have more molecules, more motions, we should end up with a higher entropy in the end. So the last thing we're going to cover here is looking at this equation here where you have delta S of a system and delta S of the surroundings. So we understand that for irreversible processes, the change in the entropy for the universe is greater than 0. Now, when we look at individual systems, the system itself can be a positive increase in entropy, or it can be a negative increase in entropy. Now let's look at a few examples that pertain to how the entropy might change for a specific system. So we're going to focus on this first one where we have iron reacting with oxygen gas, producing the iron 3 oxide. So as we can see in the reactants of this, you have a solid and you have a gas. And both of these react together to form a solid in the products. Now, from a standpoint, we need to know what type of reaction this is, and the type of reaction is going to oftentimes help us to figure out how the entropy might change for that particular system. So, in this case here, we go. This is a combination reaction, and so combination also refers to synthesis, if you've heard it that way too. Synthesis is where you take two things to make one. So going from 2 to 1 in this particular case, that's going to be going down. It's going to be decreasing the disorder in the system. And so that being the case, it's going to mean that the entropy of the system is going to go down. So that means it's going to be less than 0. Now, if we look at our second example with the hydrogen peroxide forms water liquid plus oxygen gas. So now this would be an example of a decomposition reaction. And as we look at the water, or at the hydrogen peroxide, it produces water liquid and oxygen gas. Now gases, if you understand the entropy part, gases are going to have higher entropy than the liquids and the aqueous are going to possess. So, on top of that, it goes from 2 reactants to 3 products if you just count in the coefficients for the balanced equation. So, in this example, the entropy of the system is going to be greater than 0 because it's breaking down, becoming more disordered. Now, if we look at our third example and we focus on the physical states, we have gases for the reactants, we have gases for the products, and we also focus on the number of moles. Since they're all the same physical state, there has to be something that separates this that helps us determine whether it's going to increase or decrease, or could potentially stay the same entropy and not change. So we look at the 2 reactants. The sum of those gives me 2 moles of reactants, and then I look at the products and I see that there's 2 moles of products. So the number of moles does not change. The physical state does not change. So for the entropy of this system is going to be equal to 0 because there's no change that takes place. So we're going to have to focus on a few things. And the recap of this is we have to pay attention to the type of reaction that we're working with. And so we see that this one is a combination reaction, and the entropy of the system decreases because of how we observe the number of moles plus the physical states. The second reaction, we looked at the type of reaction, which was decomposition. So decomposition means it's decomposing, it's breaking down. So we can see that in the products here. So the entropy of the system is going to increase for that. And the last one, not necessarily, the type of reaction doesn't help us determine what happens to the entropy. What we had to pay attention to were how many moles of reactants and how many moles of products there were, and the physical state that each of those possessed. Them all being the same physical state. We didn't see a change in either part, so the entropy of that system is equal to 0. Now, I'm going to throw a question up for you guys. It's just a spontaneous question. Haha. We have 4 moles of HCl reacting with oxygen gas to form 2 chlorine gas molecules plus 2 water gas molecules. My question for you right now is, what is the entropy of this system equal to? Is it equal to 0? Is it greater than 0? Or is it less than 0? So let's figure out what that's equal to. I'm going to give you guys about 30 seconds to look at this, and then we'll go over it. All right, go ahead. 30 seconds starts now. All right, that's 30 seconds. If you said that entropy was less than 0, you are correct. The reason for that being the case is if we look, they're all gases the whole way across. So we have to focus on the number of moles of reactants compared to products. So there are 5 moles of reactants and there are 4 moles of products. That means that it's becoming more ordered, and more ordered means the entropy of this system is going to go down. Okay, so in the next video, we are going to be studying entropy on the molecular scale, and we'll be focusing on Boltzmann distribution and Boltzmann's equations. So, all right, thanks for watching.